Hello everyone, welcome to section 7.5. What we're going to be doing in this section is, well, solving more trig equations. What we're going to be doing in this video that differs from section 7.4 is these type of equations just have some tricks that we need to be aware of. So sometimes we might have to do some trig substitutions, sometimes we might need to square both sides, use trig identities. So I'll show you the tricks of the trade. So let's do a couple examples. Okay, so our first one is, let's say we want to solve 2 sine squared of x is equal to 1 plus 2 cosine squared of x. So whenever we're solving any sort of trig equation, we're really just trying to somehow break it down so we just have a series of basic trig equations to solve. So looking at this one, you might think, okay, well, there are trig functions being squared, so you might try to isolate one of those trig functions that are being squared, except there's a sine and a cosine. You might try to see that this is quadratic in form, but again, the main problem is that we have sines and cosines. We would like to just have one of them. So what we're going to do here is we're going to make a trig substitution. We want this to be all in terms of sines or all in terms of cosines. So if we recall, something that will be useful for us is remembering that sine squared of x plus cosine squared of x is equal to 1. So we could solve for sine squared. Sine squared of x would be the same thing as 1 minus cosine squared of x. Or we could have that cosine squared of x is the same as 1 minus sine squared of x. So we need to make one of these two substitutions. Either I need to replace sines in terms of cosines, or I need to replace the cosines in terms of sines. It actually won't matter which way you do it. Let's say we rewrite sine squared in terms of cosine squared. So let's make that substitution. So we'll have 2, we'll use a green marker. So let's make this substitution. So we'll replace our sine squared with a 1 minus cosine squared of x. And that'll still be equal to a 1 plus 2 cosine squared of x. So now let's go ahead and distribute in this negative 2. See where this leads us. So we'll get a 2 minus a 2 cosine squared of x is going to be equal to a 1 plus 2 cosine squared of x. What's great about what we have here is we only have cosine squareds now, so let's group all our cosine squareds together, and anything that has a cosine squared, let's put it on one side, and anything that isn't a cosine squared, let's put it on the other side. So we're going to go ahead and add 2 cosine squared to both sides. And we're also going to subtract 1 from both sides. So what are we going to get? We're going to get out, well, we'll have now 4 cosine squareds of x, and we're going to have a 2 take away 1, so we'll just get a 1 on the left-hand side. So divide both sides by 4, and we'll get that cosine squared of x. I'm just flipping the equation sign. So we'll get cosine squared of x will be equal to 1/4. Or if we square root both sides, we'll get that cosine of x will be equal to the plus or minus 1/2. Plus or minus 1/2. Okay. So we've broken this equation down now into 2 basic trig equations that we can solve. So I'm going to erase a little bit of this up here. Now we need to figure out when is cosine of x equal to 1/2, and when is cosine of x equal to negative 1/2. What's nice about this basic trig equation is, well, these are nice numbers on the unit circle. We can do both of these at once. We want to know when the x-coordinate is 1/2 and when it's negative 1/2. So here's 1/2 and here's negative 1/2. So it looks like we're going to get 4 different locations for this. Okay, let's see what angles we're at. And I'll do these in green. You got to hit all these spots. Okay. So it looks like we could do, what angle is this? Well, I think that's pi over 3. So we put down our pi over 3 finger. The x-coordinate is root 1 over 2 or 1/2. So we could do x. X could be equal to 1/2. I'm sorry, pi over 3. This angle here is pi over 3. So pi over 3, but if I want to get to this spot, I could add pi, or any multiple of pi. So here I'm jumping between these two spots. But we could also have x could be equal to, well, this angle right here, that's what, negative pi over 3. And I want to jump between these two spots, so plus pi k. Or you could condense these and say this is the same thing as x is equal to plus or minus pi over 3 plus pi k. And here are the solutions to this equation here. Okay. So what might be a good exercise for you to try and do here is, notice, I guess for this example, I replaced sine squared with a 1 minus cosine squared. A good exercise is, how about you do the other replacement, see if you get the same answer as if you were to replace cosine squared with a 1 minus sine squared. That'd be a great exercise for you to do. Okay. Let's check out a different flavor of problem. Let's say, as an example, we want to solve the equation. How about the cosine of theta is equal to a 1 plus the sine of theta. Say we want to solve this equation. Well, there's sines and cosines, which is a little bit of a problem. We would like to try to have this all in terms of sines or all in terms of cosines. One of the main problems we have here, though, is that I can't use that nice Pythagorean identity we had you know, I don't know. This isn't a cosine squared. That isn't a sine squared. So the Pythagorean identities won't help us here. However, what we can do to make squares happen is we can choose to square both sides. So we really want to get cosine squareds or sine squareds so we can introduce the Pythagorean identity, but since there are none, we can force them to happen by first squaring both sides. So that might be a nice trick. Sometimes it's useful. To square both sides. Okay, let's go ahead and do that. So we'll go ahead and we're gonna square both sides, and let's see what we get. Okay. So on the left, we'll just get a cosine squared. And now what we're gonna do is we're gonna FOIL out the right-hand side. So if we FOIL this out, I think we're going to get a 1 plus 2 sine of theta plus a sine squared of theta. Okay, this is great. So what we're going to want to do from here is we're going to want to use a Pythagorean identity here. So we know that red and green. We know that sine squared of theta plus cosine squared of theta is equal to 1. In this case here, we're definitely going to want to replace the cosine squared in terms of sine squared. I could really only place this sine squared here in terms of cosine squared, but I don't know what to do with the single power of sine. So what I want to do is I'm going to replace cosine squared with a 1 minus sine squared. So let's go ahead and do that. So we'll have a 1 minus a sine squared of theta. That'll be equal to a 1 plus a 2 sine of theta plus a sine squared of theta. Okay, let's see what we can do now. I don't need these parentheses, I was just kind of putting them there to display that I was making a substitution. Well, let's see what we can do. Well, notice we have a 1 on both sides, so we could subtract 1 from both sides. We could subtract 1 from both sides. Okay. It looks like I could also add sine squared to both sides. Let's do that also. Let's add sine squared to both sides. We'll have a nice quadratic. On the left-hand side, we'll have 0. So we'll have 0 is going to be equal to, what are we going to get? We're going to get a 2 sine of theta plus 2 sine squared of theta. How are we going to solve this now? Well, what we're going to want to do here is we're going to want to factor this. So let's go ahead and factor the right-hand side. It looks like we can factor out a 2 and a sine. So if we're factoring out a 2 and a sine of theta, what are we going to be left with? We're going to be left with a 1 plus a sine theta. Okay, so let's try to think about our solutions here. Well, I guess you could think that we have 3 things being multiplied to give us 0. So if we have A times B times C equaling 0, this would be like the zero product property just with 3 things. So this means that either A is 0, B is 0, or C is 0. Well, most certainly it doesn't make sense for 2 to be 0, but sine of theta could be 0. So we have sine of theta could be equal to 0. We could also have that 1 plus sine could be 0, or we could have that sine of theta could be equal to -1. Okay, these are nice numbers on the unit circle, so I think we can solve these without doing a sine inverse of both sides. So let's think about. So where on the unit circle do we get a height of 0? Well, we'll have a height of 0, I think here. This is the one your calculator would tell you, and there's also another spot over here. This one your calculator wouldn't tell you. Okay, so you'll see I'm going to be a little bit careful here. I'm not going to write 0 plus pi k quite yet. You'll see why. So for right now, our 2 solutions, I'm not going to put a plus 2 pi k on these either, but theta could be 0, about 0 radians, or theta could be pi radians. I'm going to hold on to those here just for just a second. Okay, over here, when is sine of theta equal to -1? We'll use our same unit circle. Well, what angle do we get a height of -1? I think there's actually only one location, and that's right here. So we could also have that theta could be equal to negative 3 pi all over 2. So that's this location here. So we have the 2 locations where sine is 0, and we have the 1 location where sine is -1. And I'm only thinking about it right now between 0 and 2 pi. Okay, I didn't mean to put a negative 3 pi over 2, positive 3 pi over 2. Okay, why didn't I put a 2 pi k on these yet? Or why didn't I just put 0 plus pi k? Well, we have to be a little bit careful when we square equations. We could accidentally get extraneous solutions. Squaring both sides of an equation can be risky business. Useful, but can be risky. Let me show you what I mean. We have to check our solutions. Why is squaring sometimes risky business? Well, sometimes squaring both sides can make a false statement turn into a true statement. Let me show you what I mean here. So most certainly it's true that if let's say if 2 is equal to 2. This is a true statement. If we square both sides, we'll get 4 equals 4, which is also a true statement, so no problem here. But if we start with a false statement, let's say that -2, I hope you believe that -2 is not equal to 2. If I say 2 equals 2, this is a false statement. But when we square both sides, -2 squared is 4, be equal to 4. It turns this false statement into a true statement. So when we square both sides, we might accidentally be introducing an extraneous solution. So we have to check these. You always have to check. If you ever have to square both sides of an equation, you always have to check your solutions. So let's check them. What about theta being 0? We also want to check theta. Theta is pi, and we'll also want to check if theta is 3 pi over 2. You don't want to plug them into the version squared. You want to plug them into the original equation. Okay. Well, if theta is 0, let's plug everything in. So we'll get what the cosine of 0 will equal to 1 plus sine of 0. Let's see, cosine of 0 is 1. 1 equals 1. Sine of 0 is 0, so we get 1 equals 1. This is a good solution. So we have, so this will be a good one. So maybe I'll put a plus a 2 pi k on it, and we'll hold on to it. This is a good solution. What about theta equaling pi? Okay, we'll check that one. It solves a little bit more room. Okay, well, we'll have cosine of pi will be equal to 1 plus the sine of pi. Okay, what's cosine of pi? Cosine of pi, the x-coordinate would be -1. Okay, but the sine of pi is 0, so here we get that -1 is equal to 1. This is a false statement, so this is an extraneous solution that we picked up when we squared both sides. This will not work. Notice here, when you do plug in pi, for example, you get -1 equals 1, but when you squared both sides, you got 1 equals 1, and that's why this solution popped up. It's this extraneous solution. Okay, this one won't work. Okay, let's check 3 pi over 2. Let's check 3 pi over 2. So cosine of 3 pi over 2 being equal to 1 plus sine of 3 pi over 2. Okay. Cosine of 3 pi over 2, so the x-coordinate here is 0, will be equal to 1 plus sine of 3 pi over 2. The y-coordinate at 3 pi over 2 is -1, so we get 0 equals 0. This is a good solution. So 3 pi over 2 plus 2 pi k. So here is the solution set to this equation here. So squaring both sides is a very useful technique. You just have to be careful because you can introduce extraneous solutions. Okay. Let's try another problem. See if we can grab a better black marker. How about you try the following? Let's try to solve, how about sine of x plus cosine of x is equal to 1. Go ahead and pause the video and give this one here a shot. Okay, so there are, I think, 2 good ways we could solve this problem here. Okay, I think the thing to notice here is that we have a sine and a cosine. They both are just single powers of sine and cosine. We would like to get this all just in terms of sines or cosines. We could do that if we were able to use the Pythagorean identity. So we need to introduce sine squareds and cosine squareds. So one thing we could do right off the bat is just square both sides. So let's try squaring both sides. If we expand the left-hand side, we'll get a sine squared of x plus, we'll get a 2 sine of x cosine of x from the O and the I in FOIL, and we'll get plus a cosine squared of x, and that's all going to be equal to 1 squared, or just 1. Okay, well, right off the bat, let's notice that the Pythagorean identity is yelling at us. Sine squared plus cosine squared, that smells like a 1 to me. This and this, you add them together, you get out a 1. You gotta love that. Okay, so we get a 2 sine of x, cosine of x plus 1 will be equal to 0. I'm sorry, will be equal to 1. Notice that we could subtract 1 from both sides. So these 1s will go away. So we just have that 2 sine of x times the cosine of x will be equal to 0. So this is saying here that either sine of x could be 0 or cosine of x could be 0. I guess you can notice that 2 is never 0, or you could divide both sides by 2 and that would cancel out. But we have that sine of x could be equal to 0, or we have that cosine of x could be equal to 0. Let's draw a unit circle for these. These are nice numbers on the unit circle. Now we just need to use our calculator. Okay, when is the height 0? Well, for this one, we go do this one in green. Okay. Sine is 0 here and here. Okay, let's write these down separately. So x could be 0, or x could be pi. When is cosine 0? When is the x-coordinate 0? We'll do these ones here in red. Well, that's here and here. So x could be pi over 2, or x could be 3 pi over 2. Okay, we need to check our solutions. So let's go ahead and do that. Sine of x plus cosine of x equal to 1. Okay. Let's check x equals 0. So if x equals 0, let's see, what if we plug in zeros in here? We have 0 and a 0. Well, sine of 0 is 0. Cosine of 0 is 1. So we get 1 equals 1. So this is a good solution. Sweet. You checked this one. Okay, let's check pi. Okay, so what if we put a pi in here? Okay. Well, sine of pi is 0. Cosine of pi is -1. So we get -1 equals 1. That is a false statement. So this is not a good solution. Cross this one out. No good. Let's check pi over 2. Let's check pi over 2. Okay. Sine of pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. We get 1 equals 1. That's a good solution. Okay. Let's check 3 pi over 2. So what if we put a 3 pi over 2 in here? Okay, what will we get? Let's see, we're going to get, what is sine of 3 pi over 2? Sine of 3 pi over 2 will be -1. Cosine of 3 pi over 2 will be 0. So we get -1 equals 1. Frowny face, that's no good. All right, so we have our solution. We have that x could be equal to 0. Could be 0 plus 2 pi k. Or you could just put x is equal to 2 pi k. Or we have that x could be equal to pi over 2 plus 2 pi k. And here is our solution. Okay. Let me kind of show you a different way maybe to solve this problem if you wanted to. Show you it'd still work out. Okay. So we had sine of x plus cosine of x is equal to 1. Maybe we decided to write it like this. Maybe sine of x is equal to 1 minus cosine of x. Maybe we decide to square from here. So let's square both sides. So here we'll get a sine squared of x is equal to, what will happen here? This will be a 1 minus 2 cosine of x plus cosine squared of x. Okay? So if this is definitely not going to be the cleaner way to do this problem, but if we're looking at this here, what can we do with this problem? Well, we could decide to write sine squared maybe in terms of cosine squared, so we can make this substitution. Let's write this as a, how about a 1 minus cosine squared of x. Okay, this would not be the cleanest way to do this problem, but it would still work. Okay, so let's see here. These parentheses here aren't needed. Cross these out. Okay, we could subtract 1 from both sides, so these will cancel each other out. And we could also add, cosine squared to both sides. So this would be 0 will be equal to a negative 2 cosine of x plus 2 cosine squared of x. Okay, if you want, we could divide out the 2, or we could just factor. We could do that too. Let's go ahead and factor out a 2 and a cosine. So a 2 cosine of x. And what will we be left with? We'll be left with a negative 1 plus a cosine of x. Okay. So from here, hopefully we could see that we could get that either cosine of x could be equal to 0, or we could have that cosine of x could be equal to 1. Okay, when is cosine of x equal to 0? When is the x coordinate 0? Well, that's here. That's here. And here. Okay. And what about when cosine of x is equal to 1? Where is that happening? Well, that happens only right here. Okay, so we could have that x. X could be equal to what? Pi over 2. X could be equal to 3 pi over 2. Or we have that x could be equal to 0. Okay, we actually already checked quite a few of these. So what we found I think we found that 3 pi over 2 here didn't work, and I think we found that 0 and pi over 2 did work. So add 2 pi k. Notice that we're getting the same exact solution. We just approached the problem a little bit differently. I wouldn't say we did it the cleanest way here, but if you decided to take this route, or maybe the original equation presented itself as sine of x equals 1 minus cosine of x, and then you square from there, notice we'll get to the same place, which is great. Okay, let's try another problem. Let's try this one here. Let's try to solve the tangent of theta minus 3 times the cotangent of theta will be equal to 0. Let's give this one here a shot. Okay, what to do with this problem here? Well, if things were being squared, you might be able to use one of those nice Pythagorean identities, with tan squared, but the Pythagorean identity with the tan squared has a secant squared in it. So I don't know if that'd be super helpful for us here because we have a cotangent. What actually might be really useful for us to try here is to write everything in terms of sines and cosines, and I think that's the route we're going to take. So let's write this in terms of sines and cosines. So tangent, this is the same thing as sine of theta all over cosine of theta, minus, this will be 3 times what? The cosine of theta all over the sine of theta. And we want to know when this here is 0. Okay, so how are we going to solve this? Well, what I think we could do here is we have an equation that involves fractions. So we could clear the fractions by multiplying both sides by sine times cosine. Let's multiply both sides, clear those fractions, multiply both sides by sine of theta times cosine of theta. Okay, so let's see what happens. This will distribute into the parentheses. Okay. So the cosines will cancel out, and we'll just get a sine squared. So here we'll get a sine squared of theta minus, okay, here the sines will cancel, and we'll just get a minus 3 cosine squared of theta, and that's all going to be equal to 0. Okay. What should we do from here? Let's see. Well, we have sine squareds, we have cosine squareds. This is a subtraction sign. I would like this to all either be in terms of sines or cosines. So in this case here, let's write this as, well, let's replace sine squareds with cosine squareds. So let's replace sine squared with how about a 1 minus cosine squared of theta, okay, minus a 3 cosine squared of theta. Okay, so what are we going to get? These parentheses here aren't really doing anything. So we'll have a 1 minus 4 cosine squared of theta will be equal to 0. Okay. Or if we solve for cosine squared, I think we'll get that cosine squared of theta. Let's see. Add the 4 cosine squared to the right-hand side, divide by 4. This will be equal to 1/4. Or if we square root both sides, I hope you see that we could get the cosine of theta could be equal to 1/2, or that the cosine squared of theta could be equal to negative 1/2. Oh, cosine could be equal to negative 1/2. Okay, so let's write down the solutions here. I think we've done this one fairly recently. Okay, so when is the x coordinate 1/2? Here's 1/2. Here's negative 1/2. So we want to think about these 4 locations. Okay, so I think we'll have what? We'll get we get that theta. Theta could be equal to, what is that? Pi over 3. Pi over 3 plus pi k. But we also could have negative pi over 3 plus pi k, so we could get plus or minus pi over 3 plus pi k. So here are the solutions. Here are the solutions for this equation here. Okay. So a good thing to note for this problem specifically is what might be useful sometimes is to write things in terms of sines and cosines. And if you see that we have now an equation with fractions, you may want to try to clear the fractions to solve the equation. I also should have noted we should have been a little bit careful here. Notice specifically that cosine of theta cannot be equal to 0. And similarly, that sine of theta cannot be equal to 0. We would be a little bit worried if that popped up, but once we solved the equation and we got down to our basic trig equation, I never got that cosine was 0 or sine is 0. But you may want to keep this in the back of your mind. When I multiplied both sides by sine of theta and cosine of theta, I had to make sure to note that cosine of theta couldn't be 0 and sine of theta could not be 0. So be a little bit careful. Okay, let's try this next example. For the next series of examples we're going to do here, we're going to look at trig equations that have a period other than 2 pi. Notice here that we have 2 times sine of 2 theta is equal to 1. If we're thinking about the function sine of 2 theta, this does not have a period of 2 pi. This has a period of 2 pi divided by 2. This actually has a period of pi. So how do we solve equations like this? What I like to do, just to make sure we don't make any mistakes, is I like to make a substitution. So you don't have to do this, but I think it helps alleviate mistakes. Let's let phi be the same thing as 2 theta and make a substitution. So let's say here that 2 times sine of phi is equal to 1. And so now we're going to go ahead and solve for phi. Okay, we could divide both sides by 2. So we'd have that sine of phi would be equal to 1/2. Okay, we could do sine inverse of both sides. Okay. But 1/2 is a nice number on the unit circle, so we don't need to use our calculator for this one. Okay, we're looking for when the height is 1/2. So that'll be right here. Here's 1/2. Okay. And I believe this angle here will be pi over 6. If you put down your pi over 6 finger, the y-coordinate will be √1/2 or 1/2. So we have this location here. This is the one your calculator will report, but we also have this location here we need to think about. So we have that phi could be pi over 6, but any 2 pi multiple of that, plus 2 pi k. But we also have that phi could be equal to, how about we take pi and subtract a pi over 6, or think about 6 pi over 6, which is the same as pi, and take away a pi over 6. So we'll be at 5 pi over 6 plus 2 pi k. But be careful here, we're not actually trying to solve for phi here, we're trying to solve for 2 theta, so we need to substitute phi for 2 theta. So here we have 2 theta will be equal to pi over 6 plus 2 pi k, or we'll have that 2 theta will be equal to 5 pi over 6 plus 2 pi k. And now we can finish solving for theta by multiplying both sides by 1/2. So we get our solution would be theta, so we're going to multiply both sides by 1/2. So theta is going to be equal to, make sure to distribute this 1/2 into both pieces. So theta is going to be equal to pi over 12. Pi over 12 plus pi k. And here we'd have theta would be equal to, this will be 5 pi over 12 plus pi k. And here we have our 2 solutions. So I think one of the most common mistakes I see with students doing these type of problems here is if they don't make the substitution, they might say, okay, they say, well, this means that 2 theta will be equal to pi over 6. Then you solve for theta, and that'll be what, pi over 12, and then they say, oh, now I'll just add the 2 pi k. This is not true. This is a mistake. We have to be a little bit careful here. A good thing to notice here is that the period of this function, sine of 2 theta, is pi. So it should make sense that we should be adding multiples of pi and not multiples of 2 pi. So be very careful. Again, that's why, just to alleviate that mistake, I like to substitute the 2 theta for a phi. I solve for phi, I make sure to add the 2 pi k, and then I replace the phi with the 2 theta and multiply both sides by 1/2 to realize that I should have pi over 12 plus pi k, not 2 pi k. So be a little bit careful. Okay, let's do another example. Okay. Let's have you try to solve. How about the square root of 3 times the secant of 4 theta minus 2 be equal to 0. Go ahead and pause the video and give this one here a shot. Okay, let's do it. The first thing I'm going to do is I'm going to isolate the secant of 4 theta. Or what might be nice here is to automatically make a substitution. And you don't have to do this, but I find it to be useful. Let's define phi to be 4 theta. So we'll have the square root of 3 times the secant of 4 theta minus 2 will be equal to 0. Okay, if we solve for secant, oh sorry, I meant to replace the 4 theta with a phi. So if we solve for secant of phi, we'll get that secant of phi will be equal to add 2 divide by root 3. And we don't have, or it's not very convenient oftentimes to work with secant, so I'm going to reciprocate both sides. So if we reciprocate both sides, we'll get that cosine of phi is equal to root 3 over 2. So we need to solve for phi, so let's look at the unit circle. Okay, we want the x-coordinate to be root 3 over 2. Okay, so we put down our pi over 6 finger. We put down our pi over 6 finger. That'll be when the x-coordinate is root 3 over 2. So we could have, I guess this is what your calculator will spit out. But we want to find both. We want to find both locations where the x-coordinate is root 3 over 2. This is the one your calculator will tell you, and this is the one we have to think about. Okay, my circle's not perfect here. But this should be pi over 6, and this would be negative pi over 6. So phi could be equal to, we could do pi over 6 plus 2 pi k, or we could have negative pi over 6 plus 2 pi k, but let's just glue these together and say it could be plus or minus pi over 6 plus 2 pi k. But again, we're not solving for phi here. We're trying to solve for theta, so let's make that replacement. So here we'll have 4 theta is equal to plus or minus pi over 6 plus 2 pi k. So let's go ahead and multiply both sides by a fourth. So we'll get that theta will be equal to, this will be plus or minus pi over 24 plus 2 divided by 4 would be 1/2. So how about pi over 2k? And here is our solution set. Okay, let's do another example. Okay. Let's say we want to solve. How about cosecant? How about cosecant of theta over 2 is equal to, how about 4 times the sine of theta over 2? Go ahead and pause the video and give this one a shot on your own before we do it together. Okay. For this situation here, I think it's going to be really nice of us to get rid of that cosecant and turn it into a 1 over sine. So let's write this as a 1 over the sine of theta over 2. Actually, what might be nice to even before we do this, and since this is theta over 2, let's say phi is the same thing as theta over 2. So we'll have cosecant of phi is going to be equal to 4 times the sine of phi. Now let's write our cosecant in terms of sine. So this is 1 over the sine of phi will be equal to 4 times the sine of phi. Okay. To solve this equation, we should notice that this equation has fractions in it. Whenever you see an equation with fractions in it, clear them. Clear them. So let's multiply both sides. Let's multiply both sides by sine of phi. We should also kind of make a mental note here that sine of phi cannot be 0. I don't know if we'll need that, but let's be a little bit careful. We should note that sine of phi cannot be 0. Kind of keep that in the corner. Otherwise, we'd be dividing by 0. Okay, so what happens, on the left-hand side, we're just going to get a 1, and on the right-hand side, we're going to get a 4 times a sine squared of phi. So here we'll have that sine squared of phi will be equal to 1/4 if we divide both sides by 4. Or if we square root both sides, we'll get that the sine of phi could be equal to 1/2. Or we could have that sine of phi could be equal to negative 1/2. Okay? On the unit circle, when do we have a height of 1/2? When do we have a height of 1/2? Okay. I think again, this is at pi over 6. We're getting this pi over 6 a lot today. So yeah, if we put down our pi over 6 finger, that's when we get 1/2. But we also want what? Not only 1/2, but negative 1/2. We also want negative 1/2. So here's negative 1/2. Okay. We need this location. We need this location. We need this location, and we need this location. We need these 4 spots. Okay, so let's see here. So we could get that what? Phi could be equal to pi over 6. Pi over 6, let's see, plus pi k. Or we could also get, I guess we're right here at negative pi over 6, we could get negative pi over 6 plus pi k. So how about instead of pi over 6, we could do plus or minus pi over 6. But remember, it's not phi that we're actually looking for here. Phi is the same thing as theta over 2. Theta over 2 will be equal to the plus or minus pi over 6 plus pi k. Plus or minus. So to solve for theta, we'll multiply both sides by 2. So let's move that over here. Notice we didn't have a situation where sine of phi was 0, so I erase that. Okay, so our solution is going to be that theta could be equal to, well, if I do 2 times pi over 6, that'll be what? Plus or minus pi over 3, and we're going to get plus, we'll get plus 2 pi k. So here is the solution set. Okay, let's do one more problem. Okay, let's say we want to solve. Let's say, how about the tan of 3 theta, let's say plus 1, is equal to, how about the secant of 3 theta? Go ahead and pause the video and give a shot at solving this here. Okay, I think there are a couple good ways we could solve this one. What I'm going to do here is, let's first, since this is a 3 theta, let's go ahead and let phi be the same thing as 3 theta. So this becomes the tangent of phi plus 1 is equal to the secant of phi. Okay, I think there are 2 good approaches here, and I'll actually show you that they will both give us the same answer. One thing is we could recognize that secant and tangent are related through the Pythagorean identity. So if we remember that sine of phi squared plus cosine squared of phi is equal to 1. If we want a tangent to appear, let's divide both sides by sine squared, or sorry, by cosine squared, so we'll get that tan squared of phi plus 1 will be equal to secant squared of phi. So maybe we want to try to use this. So we're going to try to maybe square both sides. So let's take that approach. Let's go ahead and try squaring both sides, and let's see what happens. Okay, on the left-hand side, if we expand this, we're going to get a tan squared of phi plus a 2 tan of phi, that'll be from the O and the I in FOIL, plus a 1 squared, or just plus a 1, and that'll be equal to a secant squared of phi. Okay, so it would be nice for these all to be in terms of tangent. So let's go ahead and replace secant squared in terms of tangent. So let's make the substitution. Let's say that tangent squared of phi plus 2 tan of phi plus 1, that'll be equal to, let's see what, a tan squared of phi plus 1. So maybe I'll put parentheses here just to show this is where I made the substitution. But really these parentheses aren't doing anything for us. Okay, well, what do we notice? Well, notice that we could subtract tan squared from both sides, so these will cancel each other out. And we could subtract 1 from both sides, so these will cancel out. So we're just left with 2 times the tan of phi. 2 times the tan of phi will be equal to 0. Or we just have that the tan of phi, if we divide both sides by 2, tan of phi will be equal to 0. Okay, we got to be a little bit careful here because remember we squared both sides, so we are going to have to check our answer. So for what values of phi is tangent 0? Well, that'll be here and here. These are the two locations where the slope is 0. Let's write down these each separately. So we have that phi. Looks like phi could be 0 radians or phi could be pi radians. Okay, let's plug that into our equation. Let's plug this into our equation to solve this. So let's plug it into the one where we substituted in phi. So let's erase a little bit of this here. We'll check it right here. Okay. Well, if phi is 0, okay, this would be the tan of 0 plus 1. I'm not super familiar with working with secant. How about we write this as a 1 over the cosine? So that'd be 1 over the cosine of 0. 1 over the cosine of 0. Okay, on our unit circle. Okay, cosine of 0 is 1. So what is this? Tan of 0, the slope here is 0, so this would be 0 plus 1 will be equal to 1 over 1, which is 1. 1 equals 1. Happy face. This one here will work. Okay, but what about pi? What about pi? Okay, what if we put a pi in here? Okay, well, tangent of pi is still 0, but cosine of pi is negative 1. So here, this is 1 over negative 1. So this is 1 equals negative 1. This is not true. Frowny face. This is not a good solution. Okay. So we have that phi could be equal to 0 plus 2 pi k. This is a good solution. But phi is the same thing as 3 theta. So 3 theta will be equal to, instead of 0, how about we put 2 pi k, multiply both sides by a third, we get that theta will be equal to 2/3 pi k. And here is our solution set. Okay, maybe you took a different approach on solving this problem. Maybe you didn't square both sides from the beginning. Let's maybe take a different approach. Let's take a different approach. Okay. I'll still make that substitution that 3 theta is phi. But maybe you are uncomfortable working with tangents and secants, so maybe you want to write this in terms of sines and cosines. So here, we could have that sine of phi over cosine of phi plus 1 would be equal to 1 over the cosine of phi. Okay? And maybe you notice that, hey, oh my goodness, like, I got an equation with fractions. Let's clear them. Let's clear them. Maybe we decide to multiply both sides by the cosine of phi. Okay. So this cosine of phi will distribute into the parentheses. And what will we get? We're going to get a sine of phi plus a cosine of phi is going to be equal to 1. Okay. We should also, I guess, kind of mentally note here that cosine of phi cannot be 0. Cosine of phi cannot be 0, otherwise we'd be dividing by 0. Okay, so it looks like to solve this one, we've seen something similar like this before. We're still going to have to square both sides for this one. So let's go ahead and do that. Let's go ahead and square both sides. Let's see what happens. Okay, so when we square both sides, we're going to get what? We're going to get a sine squared of phi plus a 2 sine of phi cosine of phi, that's from the O and I in FOIL, plus a cosine squared of phi will be equal to 1. Do you smell it? I smell a 1. I smell a 1. Cosine squared plus sine squared. And you add those together, you're going to get out a 1. So, looks like we have 2 sine of phi cosine of phi. This will be what? Plus 1 will be equal to 1. Right? So we could subtract 0 or we could subtract 1 from both sides, so these will cancel each other out. So we have 2 times the sine of phi times the cosine of phi will be equal to 0. Okay, so this says that sine of phi could be equal to 0, or that cosine of phi will be equal to 0. But, good thing we made this mental note over here, cosine of phi can't be 0 because we'd be dividing by 0, so this cannot work. Okay? If you didn't write this down initially, you could have figured out the values of phi that make that make cosine 0, and when you actually substitute them back into the equation, you would have found that those solutions would have been no good. Okay, so we just need to look for when cosine of phi is 0. Let's leave ourselves some room. Okay, so we just need to think about when is sine of phi equal to 0. Okay, well let's look at the unit circle. Okay. Where do we get for what value of phi is the height 0? Well, that'll be here. That'll be here. This is the one the calculator would tell you. This is the one the calculator wouldn't tell you. Okay, so we could have that phi. That phi could be 0, or that phi could be pi. Okay, so we would want to make sure to check these, and I think we already checked pi from the last problem. I mean, we could check it again. Well, I think we found, we plug in 0, if we plug in 0 here, we plug in 0 here. This is the same as 1 over the cosine of 0. Okay, so tan of 0 is 0, 0 plus 1 is equal to cosine of 0 is 1. We get 1 equals 1. This is a good solution. If we plugged in pi, well, tangent of pi is 0, so 0 plus 1, but this is going to be a 1 over cosine of pi is -1, so you get 1 equals -1, which is a false statement, so this solution here is no good. So remember, it's not phi we're looking for. Phi is the same as 3 theta, or I would say phi could be 0 plus 2 pi k, but phi is the same thing as 3 theta will be equal to, how about just 2 pi k? You can multiply both sides by 1/3, so you get theta would be equal to 2/3 pi k, which is the same solution we had with our first method here. I love doing problems in different ways and just really seeing that, math works. It's fun exploring different ideas, getting to the same solution. I don't know, makes me feel good. Okay, that's all I have for this video. What we're going to be doing in the next video is we're going to be looking at trig equations where maybe we have like a sine of 2 theta and then we just have like a sine of theta. So kind of a trig equation where the periods aren't matching up. We'll see you there. Take care.